at the entire shaft. If we use what we talk about on the shaft, so this shaft is carrying bending moments from the side, twisting moment from the side at the same time. And from the yesterday's lecture, we mentioned this point carries more loads than the point on the side, because the one on the side is on the neutral plane for bending. So there's no normal force left to right. But the one on the top, because we are bending down, so over here it's being stretched along the x direction. So we can use the information over there and try to study the shaft, the stress inside the shaft. Okay, so like I said earlier, and also what you have learned, this doesn't help us enough. Because if we observe this particular point in a different coordinate, it's possible to rotate the coordinate to a different angle. And over there, we can see even greater normal stress, which is the principal stress. So the trick is basically Mohr circle. So if you focus on this particular point and observe from the top, you have this diagram highlighting the stress along the current coordinate, x, y, and z, not y, x, and z. So you can actually change the angle of your view, change to a new coordinate, then you should see greater stress. So in general, the process of Mohr circle is like this. I didn't use the same coordinate system as the previous one, but same loading condition. So what you are going to, if you forget about Mohr circle, let me remind you. So you are going to walk around the element, and you can start from any point. So you can pick up a point on the edge right here. For example, the one on the right hand side, let's say point A, and you can try to see what kind of load this position is carrying. And let's try to keep a record of the stresses that are being applied on this particular point using the diagram on the right. So what's going on for the diagram on the right? For the horizontal coordinate, we're going to record the normal stress that is applied to the position you are studying. And for the vertical coordinate, you are going to study the shearing stress. But for shearing stress, there are directions. So the positive and negative for normal stress and the positive of negative of the shearing stress represent something, represent some kind of direction. So in my drawing, in the current demonstration, if I see normal stress coming out of the element, I treat it, basically that's tension, right? Pulling. So I decide positive value represent tension. You can define your own way, but that's the usual way. Okay, so positive stress represent tension. And also over here, there are many different people use different ways to record the shear stress because some people like clockwise as positive, some people like counterclockwise as positive. So it doesn't matter. In my demonstration, I choose counterclockwise as positive. So whenever you see a shearing stress that's like rotating counterclockwise about the center, then we treat it as a positive shearing stress. So over here you can see there's a positive normal stress, sigma A, and there is a counterclockwise shearing stress tau A with some value. Okay, so there are positive values. Then you should have a point right here. So this is the amount of normal stress right at the point A, and this is the amount of shearing stress right at point A. So you can say, okay, this is the low condition at position A. Okay, now, the investigation at the first point is done. You can start to change your position. You can now move to a different place like here. So over here it's important that you made a 90-degree change on the element. So it's like you walk around the element and you make a turn. You change the direction of your investigation. So the direction of your investigation was rotated by 90 degrees in the real world. And over here you see there is a clockwise shearing stress. So in the way of I keep in record of the stresses, this is a negative value. But it's the same magnitude. The only difference is that it's changing its direction. So over here, the shearing stress would be negative tau A. That's why we have a negative tau A right here. And how come it's on the vertical axis? Because at this particular point, there's no normal stress. So normal stress equals to 0. That's why sigma B equals to 0. And tau B is equals to negative tau A. So that will be our second investigation point. I highlight it as B. Now if you change your investigation point to a third point right here, you will realize, hey, basically it's a normal stress of tau A and a counterclockwise of shearing stress, sigma A and then counterclockwise tau A. Again, exactly same amount. So you will see the low condition right here on the left is exactly the same of the low condition on the right. So when you are investigating this point, you actually will keep a mark at the same position. So then you realize if you make a 90-degree turn in the real world, in the Mohr circle coordinate, you already made 180-degree turn. Okay, so that when you move to the opposite side from the starting point to the left, you already turn 180 degree in the real world, but in the Mohr circle, you already turn 360 degree. Okay, that's why usually for Mohr circle, you only need to investigate 2 points. You don't need to investigate the other 2 because they will be the same point in the Mohr circle diagram. Okay, so you can make a circle like this. Whenever you turn theta degree on the left in the real world, in the Mohr circle coordinate, you will be making a turn of 2 theta degree. And for every position on the circle, basically that would be the low condition for the element in different angles. Then you realize there is a point right here where you will have the largest normal stress. And there's another point right here, this position, you have the smallest normal stress, the most negative normal stress. So that would be the position that we are looking for. So if you now focus on the Mohr circle and try to change the observation angle by 2 theta degree, you move from this point A to a point D. So over here, you change the angle by 2 theta. In the real world, you will be changing the observation angle by theta. So if you change the coordinate by theta, like making a clockwise rotation by theta, you move on to a new coordinate, we call it x prime right here. So now you are like, earlier you are observing the element straight. Now you just bend your head and then observe the whole thing in a new coordinate system, but still the same element. If you observe the element in this way, then the low condition is gonna be like what I'm drawing right here. Because the Mohr circle tells you, if you observe the element in this angle, that position is going to carry a normal stress of S1, no shear stress. So if you observe that point in this way, there's a normal stress of S1, no shear stress. And we call this one a principal stress. Similarly, in this new coordinate system, if you from here and make a turn by 90 degrees, you move on to a new point E. In a Mohr circle, you will be making a turn of 180. So now you move on to this point E. And the Mohr circle tells you, on this point E, this element is going to carry a negative normal stress, no shear stress. That's why this angle, point E, is carrying a compression stress. And it's the second principal stress. Okay, so S1 in this condition, based on the drawing I made, along this observation angle, horizontally is carrying the largest normal stress, S1, and vertically is carrying a most negative normal stress, a compression stress. So here, if you observe the element in this way, you don't see shearing stress. So usually, we will make our design based on this angle. Because we need to know how the element is carrying the most loads. And we want to check if that largest load is greater than our strength. So if you observe in a different orientation and it's actually telling us it's not carrying this much load, then we will underestimate the load. So we may basically, we will have a lower design than safety. Lower design than safe design. So which is not good. That's why we want to use Mohr circle to find out, basically along this orientation, this element will be carrying this strong load, a tension load in this direction, this amount. So let's worry about this. Okay. And also, we also care about what is the orientation where we will be carrying the largest shearing stress. So based on this x prime, y prime coordinate, if I rotate the coordinate by 45 degrees, which means in the Mohr circle, we will be making a 90-degree turn from the principal stress. we will move on to a new point F right here. This is the position that we have the largest shearing stress. So if we, again, originally we are viewing the element straight, I turn a little bit to find out, okay, along this angle, I see the largest normal stress. Now I turn the coordinate by 45 degrees again, then I observe this kind of low condition in this orientation. And I realize if I observe the element in this way, at every edge it's carrying the maximum shearing stress. Okay, and maximum shearing stress is very important for our design as well. So the amount will be tau max, basically the radius of the Mohr circle. Okay, so once you understand this, next will be how do we compute those? So the radius of the Mohr circle can be easily computed by the square root of the sum of these two square terms. One is this part, the square of this part, and square of this part. So first part, basically, this will be right here. This point is sigma A, right? So I only need half of it. So this distance from the center of the Mohr circle to this position is basically half of sigma A. This is sigma A, right? This is sigma A, but this is only half. That's why square of that distance is gonna be sigma A squared over 4. And the height right here basically is tau A. That's why we have a tau A squared. And you sum them up, take a square root, then you will get the radius of the Mohr circle. That's gonna be exactly the same as your tau max. Okay? Now, how do we compute the first principal stress and the second one? Basically, over here, this is half of sigma A plus the radius, then you have S1. Minus the radius, you have sigma 2. That's why you have half of the sigma A plus the radius, half of sigma A minus the radius. That's how you can compute S1, S2, and tau max. Should be pretty easy. Okay, now, earlier I showed you the example where we don't have normal stress along y coordinate. But in general, for this planar loading condition, we may have normal stresses along the y coordinate. Then it's basically the same procedure. The only issue is for point B right here, it's not lying on the vertical axis, it's right here. In this particular example, for point B, there is some kind of amount of the compression normal stress right here. And over here, in this example, I treat it as a compression stress. So it's carrying a negative value and the same amount of the shearing stress. So the only difference between this case and the earlier case is basically in this one, tau B is not 0. The earlier one, tau B is 0. So in general, we compute the tau max, S1, S2, basically the same way. So over here, you are going to use this triangle as well to figure out the radius, okay? But how do you know this amount? This amount basically is the half of this long distance from sigma B to sigma A, right? So how do you compute length from sigma B to sigma A? Basically sigma A minus sigma B. because V sigma B is a negative value. So if you use sigma A minus sigma B, take half of it, square, then everything is the same. Everything else is the same. How about this one? This is basically the position of this center. So how do you get the center? So it's like a mean value of sigma A, sigma B. So basically it's this distance, right? So this position is basically the mean of it. That's why it's a plus sign here, not negative. So if you understand this, then it's nothing difficult for you. Okay, so that's a reminder for Mohr circle, and that will be important for the models later on. Now, I think I also need to tell you about Mohr circle for tensile test. You may not understand why we need to do this, because later on in many of our models, we will use this concept. So let's think about a tensile test. You basically have a workpiece, you use some kind of clamp, tightening the top and the bottom, and then you pull it. So the purpose of tensile test is to apply tensile stress onto the element without applying any other forces. And what's gonna happen is, the more if you make a loading diagram like this, basically the element is being stretched along certain direction. So initially there's no stress, so sigma A equals to 0. And when you start to pull the element, these amounts start to increase, but nothing else. There's no shear along this direction. There's no normal stress horizontally. There's no, if this is X and this is Y, so there's no stress along Y. So basically, this is a low condition for tensile test. And if you make a Mohr circle, it's gonna look like this. So basically, initially, the Mohr circle is like a small dot. And when you start the machine, start to pull, the Mohr circle starts to expand. But S2 remains 0. S1 basically moves toward right. Until one day, S1 reaches the yielding point. So that would be the position where we cannot, we consider this piece as failing. Because in our design, like I said yesterday, we only focused on elastic loading condition. We don't want to see nonlinear deformation. We only want to keep it inside the linear region, elastic region. Okay, so here's a very simple design concept. Maybe the element can only carry certain normal stress until the stress is reaching the yielding strength, then stop. So the most simple design concept is like this. Our first, the first principal stress should be smaller than the yielding strength. So in later on, when we talk about design, we always have some kind of equation with inequality sign. We want to make sure our design, the load we're carrying, that is smaller than our strength. So basically, this is our strength, right? And here it is basically the stress that we are carrying. And if we implement the idea of safety factor here, then we should have a equation like this. Why is that? If I put some numbers, then you can observe this more easily. Let's say I'm now, the strength of the material, for example, is a value of 100. So when I carry the stress, for example, 80, I'm safe. But if I carry 99, I'm safe. If I carry 100, then I am about to fail because the stress I'm carrying is already reaching the upper limit. So if the stress increased by one unit, then the stress now is larger than the strength. I should see yielding condition. Then the material will be nonlinearly deformed. It doesn't recover back to its own shape. So we don't want to see this situation happen. But in reality, for mechanical design, we never want to see a stress that is so close to our upper limit. Because how can you be sure if the material is ideal? So let's say this workpiece is made of steel, some kind of steel, and the manufacturer already give you a report, tell you the Young's modulus of the steel. But the manufacturer probably produce 10,000 pieces of this workpiece. He cannot guarantee every piece is the same. No one can. So there are so-called uncertainty. Uncertainty is everywhere. In Chinese, it's called 不确定性, uncertainty. So something that varies. So if you get a value, for example, what's the Young's modulus of steel or Young's modulus of copper from Google, it tells you a number. Does that mean the same material around the entire world is carrying the same Young's modulus? Actually, no. Because that's value from the internet, from the textbook, probably is just an average value. Someone did experiments thousands of times and then tell you, oh, averagely, maybe the Young's modulus of steel equals to this amount. If you are not sure, do your own experiments. So usually when you have, if you check any textbook, and when people show you the stress-strain relationship, they draw a very ideal curve like this. But what happened in reality? Maybe when you do true experiments, if you do real experiments 10,000 times, every time the result may not stay on the straight line. There are uncertain changes to the real situation. So one of your piece probably is stronger, so you can have, if you for this one, this is stronger than average, right? But for this one, for this particular experiment, it's weaker than average. So you cannot 100% control the quality of your workpiece. That's why we don't want our design to reach to the upper limit. We want to keep a kind of safe margin. So if safety factor is 1, it's basically the same equation. But now if I say I want my safety factor to be 2, and I know the average yield strength is 100, what's going to happen? The value right here is 50. When you do this, that means you only allow the stress to be as large as 50. You only want to carry stress up to 50 in this particular example. So compared to the first design equation, you realize you are allowing the stress to be as high as 100. But if you choose your safety factor to be 2, then you only allow your stress to be half of the yielding strength. So basically, you only allow your stress to be as low as 50, which is safe because you are having a huge gap between your max value and the yielding point. Okay, so from here, I hope you understand the importance of safety factor. Okay. Now, this concept is very important because later on in the model, we will, in many models, we use this exact concept to derive some equations. Okay, so I hope you remember this or understand what I'm trying to say. Okay, how about 3D cases? So actually for for most of the problem that we're solving, we're only doing a plane stress problem. So basically stress, a plane stress problem, right? So basically we only deal with 2D problems like this. Oh, okay. Only 2D, x, y coordinate. We assume there's nothing along the third coordinate. So if I remind you the real situation in the situation in the real world, there is a plane stress problem and plane. Basically, there's a planar stress problem and planar strain problem. So there are two possible situations. You have a low condition like this. So one situation is that you are really having a plate, okay? And you are focusing on XY coordinate and Z coordinate. And you don't really apply any stress along Z direction. So in this particular problem, basically sigma ZZ equals to 0. Okay? So this is the plane stress problem. And there's another case which is you have a huge object and you make a cut of a planar cut of the object, and because its neighboring plate is carrying identical low condition with your planar cut right here. So if this is the Z direction and the neighboring plate is limiting the movement, the displacement along the Z direction of this particular plate. In this case, your strain along the Z direction equals to 0. So that's why we call this a plane stress problems. Both of them are planar problems. Basically, low condition in a plane. So either one of them, if you make a force diagram like this, same diagram. But in real world, sometimes it's a plane stress problem like this, or a plane strain problem. Okay, just remind you what happened. But if you are not dealing with these two kind of problems, then in general, you may have stresses in the third coordinate. So take this, even for this plane stress problem as an example, actually there are 3 more circles. So for the XY coordinate, you have the big circle right here. This is along the XY, in the XY plane, the stress condition in the XY plane. But in fact, because your stress in the third coordinate is 0, so there is a third principal stress which is 0 right here. And if you try to investigate the load condition in YZ plane or XZ plane, you can actually draw more circles of those. At the end, you will have 2 more circles. This one is represent the more circle in the YZ plane. This one is represent the more circle in the ZX plane. So actually, there are 3 more circles. But for us, if we want to do homework, take exams, or try to study something, when we deal with 3D problems, it's too complicated. So later on, for our further analysis, we only focus on 2D problem. So I think we are introduced enough for the review of Mohr circle. I need to move on to the homework problem. I think it's this one. No. Should be this one. Is it? No. Not this one. So today we will be, I will giving you a homework, and there are detailed descriptions in my notes. So I know today I only have 1 hour, so I cannot completely go through the process with you, but I hope you still remember how to do this. So for a problem like this, there are 2 bearings at each edge of the shaft. There are 2 pulleys. And because the pulley is having a belt, so the belt has some width. So when there's a pulling force on the belt, 皮带 belt, and it's not a single load, it's a kind of a distributed load. So when we study the shear force and the moment, we basically treat it as the distributed load. So in the problem, I already give you the amount of these values. They are shown here. So they are distributed load per unit length. There's a certain amount of forces. Okay, so it's the unit is Newton over millimeter. All the units here of length are in the millimeter. Okay, so the first thing you need to do for this kind of problem is that you need to figure out the supporting forces, the reaction forces on the bearing, because these are there are load conditions in 2 different planes. So we need, in this particular case, we need to do this twice. So for balance of moment, first I focus on the XY plane. So in this case, you don't need to worry about the forces along the XZ plane. And basically, you can see all the equations that's been clearly written right here. Take the first one as an example. I think I treat the RF. I treat point A, this is a point A as the support. So W3 and W4 is providing a counterclockwise moment. And reaction force of Fy is also having a counterclockwise moment, because when in my drawing I make it positive. I assume it's a positive value at the beginning. Then you have a balance of moment like this. After the derivation, we realize, oh, Rfy is actually negative. So actually this reaction force goes down. So do balance of moments like these. At the end, you can get all the reaction forces. Next, how do we do the shear force diagram? So let's take a walk from the left to the right. Whenever you see a single force, if it's going up, then your shear force goes up. If it's going down, then it goes down. So from our previous analysis, Ray equals to -435. That's why in this diagram, when you take a walk from 0 to the position of 10, it goes down by 435. And then if you keep on walking toward right, there's no more forces along y direction anymore. So no more changes of the shear force. So the shear force remains the same until it reaches the position of here, basically point D. And then right here it's carrying W3 and W4 distributed loads going up. So if it's a distributed load, then it's gradually increasing whenever you take a walk toward right. So the total amount of W3, W4 equals to W3 plus W4 equals to 28, right? So every millimeter you move forward, the force increased by 28 because W3 plus W4. So over here, if you take a walk by 1 millimeter, the shearing force goes up by 28. So the slope right here is 28. So this kind of increment of shear force remains the same until it reaches the other edge of the pulley, and then you have a max value of 965, and then no more forces. So you keep walking until here. There's a negative reaction force goes down, and then it goes to 0. So this is how you can make the drawing of the shear force. And you can easily derive the shear forces in 3 different regions. So those are the equations for these 3 regions. The only thing is, for the second part, it's a linear equation. It's going to be 20a, the slope, times x, plus some value. So how do you get it? You can just plug in certain position. In this case, I plug in the position of 240, and then I know the shear force right here is gonna be -435.1 in order to get C1. So I know the constant value right here. So why do I decide to get the equation? Because I know if I take the integral, I can get moment. So you can easily get the moment using the integral. So taking the integral of these 3 shear forces, at the end you have these 3 equations of moments in 3 different regions. But every time you take an integral, you increase an unknown constant. So how do you get the constant value? Basically, you just plug in values at different positions. So I think I did at position of 0, the moment should be 0. So I guess C2. And over here, for the C3, I think I compute the value right here. And then plug in the second equation for this second order equation. So I can get C3. For the last one, I just plug in the point at the edge, which gives me 0 moment. So at the end, you get C4. So that's how you get the entire profile right here. And this portion right here is a second order equation. Okay, so similarly, do the same thing along the xz direction. You will end up with something like this. Okay, so to sum up, overall, the moment along y looks like this, the moment along z looks like this. So it seems like there are some extreme points. So you can try to figure out a way to find the minimum point. So how do you do that? Because they are second order polynomial, if you take a derivative and make it equals to 0, that tells you the extreme point of the second order equation. So that's how I got the position of this one. That will be the minimum point here. And this one, same trick I found at 134. I have the smallest value of this moment. But in fact, smallest value means largest moment in this negative direction. So overall, actually this position 2, 5, 6 is carrying the largest bending moment along y, and also some amount of bending moment along z. Okay? So that would be, I even plug in the values at position 1, 3, 4 and position 2, 5, 6. I realize overall, I can compute the moment total. So how do you compute the moment total? Basically, they are moment vectors along 2 directions. So what you can do is to do a vector addition. So basically, computing, basically take a square root of this plus the square root of this, sum them up, and take a square of this plus square of this one, sum, and then take a square root. Then you get the total moment. So here I show you how I computed the total moment at 2, 5, 6 and total moment at 1, 3, 4. So in fact, the position of 2, 5, 6 is carrying the most total moment. It's not along y direction, not along z direction. It's like an angular direction. So that would be for the bending moment part. How about twisting? So there, because the stress, the tension on both sides of the pulley is not the same, so it's constantly twisting the shaft. So you can compute the torque, and you will realize the torque equals to, how come this, let me explain why it's, why is it this equation. So we will basically focus on W3 and W4. W3 is 15, W4 is 13. So the difference of them is 2, right? So 2 Newton per millimeter. So the difference between them is 2 Newton per millimeter. But how many millimeter? 50. So 2 times 50. This is the force difference. What will be the radius? Radius is 37.5. So that would be the torque right here. Okay. If you do the same on here, you will see, oh, the torque is the same, because this problem was properly designed. So there is a constant torque along clockwise direction, and here is a constant torque along counterclockwise. Okay. So for the entire beam, for the center portion, it's being constantly twisted. So by this, we already know at position 256, the maximum bending moment is this amount. The maximum torque is this amount. Using the equation that we introduced last time, sigma equals to 32m over pi d cubed, tau equals to 6t over pi d cubed, we can get what will be the stress and sigma and tau at this position 256. So over here at some point 256, it's actually carrying this kind of low condition. And the stress and the shear was computed in the last page. If you draw the Mohr circle of this particular point, then you will know the principal stresses and the maximum shear stress. That will be the goal of this problem. Okay? So I want you to go home and use this one as a homework, but I'm not going to give you exactly the same problem, so I want you to make a change. The change would be, so let me move up. Sorry to occupy a little bit of your time, but I will tell you what's the homework. So let's do this. How about this here? Okay. If I change the coordinate y to a different position, everything changes. Because all the calculation will be based on this new coordinate. And you can follow exactly what has been introduced in the PowerPoint, but based on this new y coordinate. So you should get the exactly same diagram and results, but because the coordinate is different, so later on when you find the worst position, earlier it was 256 millimeter. In this new coordinate, the position will be different. So this will be a new position, new value right here, right? So just make the change of the coordinate by shifting here to here and do the exact homework. Okay, you have 1 week of doing so. Okay, that's it. Sorry that I occupy over 5 minutes. That's it for today. See you next week.